The lithium-ion battery's journey from a rudimentary-looking device to a ubiquitous power source highlights its revolutionary impact, inherent dangers, and the ongoing quest for safer, more sustainable energy storage solutions. This is what the inside of a lithium-ion battery looks like. It's not exactly high-tech. Just 2 sheets of foil coated in black paste, all packed into this tiny 45-gram cylinder. But these are some of the best batteries we have, and they power everything from laptops and electric vehicles to orbiting satellites. Yet when a battery fails, all that energy can get released in the wrong way. Oh my God, the latest incident involving lithium-ion batteries. So how did something so rudimentary looking end up in almost every electronic device on the planet? And why don't we have anything better? In the early 1980s, most rechargeable batteries were stuck at just 40 to 60 watt-hours per kilogram, meaning you would need a kilogram of battery to power a 40-watt light bulb for just an hour. As a result, when the first commercial mobile phone launched in 1983, it was pretty unimpressive. It took 10 hours to charge for just 30 minutes of talk time. Laptops, cameras, even medical devices all suffered from the same bulky batteries. Everyone from electronics giants to oil companies were trying to make a better battery because they knew that even just doubling the energy density could unlock a new era of portable electronics and power the digital revolution. In 1972, chemist Stanley Whittingham was studying energy storage at Exxon's research lab. Yes, that Exxon. The next year, the oil crisis hit. Arab producers cut off exports, and Americans queued for hours at gas stations. Worried supplies would run out, Exxon looked to electric cars, but their batteries were terrible. Suddenly, Whittingham's side project became a top priority, with free rein to find a solution. At its core, a battery has 3 main parts: an anode that gives up electrons, and a cathode that receives them. When connected, electrons flow from the anode to the cathode through an external circuit, creating an electrical current. But this flow stops almost instantly without the third component, the electrolyte. While electrons can't pass through it, the electrolyte allows charged ions to travel between the anode and cathode, keeping the current flowing. For decades, commercial batteries used a water-based electrolyte. This created a fundamental problem. Water breaks down at just 1.23 volts, setting a hard limit on a battery's voltage and its energy density. In the 1970s, chemist M. Stanley Whittingham took on this challenge. He explored materials with a layered structure, perfect for a process called intercalation, where ions could slip in and out repeatedly. He paired a titanium disulfide cathode with an anode made of lithium, a light, reactive metal. This was the first step toward a rechargeable battery that could shatter the voltage limit of water. Lithium releases more energy per electron than any other metal, producing the highest voltage. It's also the least dense metal, a perfect combination for a high-energy density battery. But pure lithium is dangerously reactive. To use it, Whittingham replaced the water-based electrolyte with a risky organic solvent. This unlocked lithium's potential, breaking the voltage ceiling and delivering 2.4 volts per cell, nearly double what was previously possible. Whittingham's prototype had a metallic lithium anode and a titanium disulfide cathode. When the circuit closed, lithium ions moved from the anode to the cathode, while electrons flowed externally, generating power. This process, called intercalation, was reversible. Applying a voltage sent the ions and electrons back, recharging the battery. Amazingly, this early prototype was nearly 99% efficient, working reliably cycle after cycle. It was the first truly rechargeable lithium battery. In 1973, Exxon invested in Whittingham's design, but the battery's pure lithium anode was prone to fires. The problem was dendrites. When charging too fast, these sharp needle-like structures could grow through the separator, creating a short circuit leading to fire or explosion. The battery was just too dangerous. When the oil crisis ended, Exxon shut down the program, and the first lithium battery revolution died. At Oxford University, physicist John Goodenough saw a limitation in Whittingham's design. The cell voltage was being held back. He believed a better cathode material could do better. He turned to lithium cobalt oxide. The voltage immediately spiked to 4 volts. Crucially, this new cathode already had lithium ions built into its layered structure. This meant the supply of lithium didn't have to come from dangerous lithium metal. It paved the way for a safe anode and a battery powerful enough for the real world. Every field has its bottlenecks. For batteries, it was slow-moving institutions. For developers today, it's slow-moving code reviews. And I can relate. When we make these videos, especially the ones with simulations or complex animations, it's rarely the ideas that slow us down. It is the reviews. Developers face the same thing. They're writing code faster than ever thanks to tools like Copilot and GitHub. But code reviews, they're still manual and still slow. In Japan, chemist Akira Yoshino was searching for a safer anode, one that didn't require volatile lithium metal. His idea was to use a carbon-based material, but he needed a source of lithium ions. He found the missing piece in a paper by John Goodenough, describing a cathode made of lithium cobalt oxide, a cathode that already contained lithium. Yoshino combined the two. To prove its safety, he dropped a heavy iron rod on a traditional lithium metal cell. It exploded. He then ran the same test on his new design. Nothing happened. That was the moment the lithium-ion battery was born. His employer took the design to Sony, who saw its potential. Sony refined the anode using graphite, and in 1991 launched the first commercial lithium-ion battery inside the Sony Handycam. It was compact, rechargeable, powerful, and safe, sparking a revolution in portable electronics. But what's crazy is that even after all this, these batteries should never have worked. See, when you charge the battery for the first time, lithium ions move from the cathode to the graphite anode, and here they react with the electrolyte to form this weird, complex patchwork of compounds that build up on the anode surface. These parasitic side reactions could keep going on indefinitely, using up all the lithium and destroying the cell. But they don't. Instead, they form a thin, protective layer known as the solid electrolyte interface, or SEI. It's a kind of chemical shield protecting both the graphite anode and the electrolyte from further reactions. But crucially, lithium ions can still slip through it. When the SEI originally forms during the first charging cycle, around 5% of the lithium in the cell actually gets stuck in this layer, decreasing the battery's capacity. But this little trade-off is what makes the battery stable enough to be used for years or even decades, which is why today, lithium-ion batteries are virtually everywhere. From 1991 to 2023, the price per kilowatt hour dropped by 99%, from nearly $9,000 to just $100. At the same time, energy density and cycle life, how many times the battery can be charged and discharged before it wears out, improved dramatically, crossing a critical threshold. Lithium-ion batteries have become powerful enough and finally cheap enough for something bigger, the return of the electric car. Today, lithium-ion powers a $100 billion industry. In 2019, Whittingham, Goodenough, and Yoshino finally received the Nobel Prize in Chemistry for an invention that, in the committee's words, revolutionized our way of life. This made Goodenough the oldest Nobel laureate in history, receiving the award at the age of 97. But lithium-ion isn't perfect. Scary moments aboard a JetBlue plane, a fire erupting after a passenger's backpack suddenly exploded. Every week there's at least one event of a battery of a phone or an iPad or a toy or something that is caught on fire. What? Every week? Yeah, every week. This is just the latest incident aboard a plane involving lithium-ion batteries. So far this year, 60 onboard battery incidents through early October. Every flight in the US has a flight-specialized fire, very thick. Non-flammable material where you put the phone inside, and you close it. And if they have a fire that you have to deal with these gases. But now, you have to put the fire ignition away from anything else. And if it bursts into fireworks, then that's an airplane, and they're going to tell the control. We need to learn immediately. But the layers inside a battery don't stay perfect forever. Here's an electrode from a new cell compared to one from an old one. You can see lithium building up in the wrong places. If this degradation gets out of hand, we get a catastrophic failure. We're simulating that by pushing this cell past its breaking point. It starts around 80 degrees Celsius, when the protective layer on the anode breaks down. The reactions release more heat, and if that heat can't escape, the temperature keeps rising into thermal runaway. The battery contains its own fuel, its own oxidizer, and its own source of heat, all in one device. It's not actually the lithium that burns, but everything else inside. While dramatic, the standards of engineering are incredibly high. For a well-made battery, a failure like this happens in less than 1 in a million cells. Thanks for watching. If you want to see more videos of invention chronicles and science, give a thumbs up and subscribe to my channel, and hit the notification bell so you don't miss any new uploads. And if you enjoyed this, please share with friends.